Well, hello everybody. I'd like to welcome you to this evening's session of Astronomy for Beginners. My name is Stephen Price from the Bristol Astronomical Society, and I'll be chairing this evening's session. On behalf of the Bath, the Bristol and the Cardiff Astronomical Societies, I'd like to welcome you all to this beginner's course for astronomy and hope that you very much enjoy the topics we're going to cover this evening. This is the second session of a six-part programme, and this evening's theme is The Secret Life of Stars. But first of all, some quick reminders on attending this evening's sessions over Zoom, please. Can everybody remain muted during the session at all times, please, so we can avoid any distractions during the talks? We can mute attendees if required, and we really appreciate your cooperation in this. If you have a question during or after a talk, then please type that question in the chat box on Zoom. We'll have a few minutes at the end of the talk to answer some of these questions, and we'll respond to all other questions after the session is closed, and we'll let you know the answer. Now, you should have received with your invitation to these astronomy beginners classes a resources pack, which had useful references, websites, videos, software and books, links to those for your information. If you haven't received that resources pack yet, then please let us know in the chat box on Zoom and we can send it to you or resend it to you after the meeting. So that brings us to our two talks for this evening. Our first talk is The Secret Life of Stars by Dr. Alison Camacho from the Bristol Astronomical Society. Just a few words of introduction for Alison. Alison has a degree in physics from Bristol University, a PhD in plasma physics from Cardiff, and is a qualified teacher of over 20 years. Alison has run an astronomy club in every school she has worked in, being one of the first teachers to use the robotic 2-meter reflecting Fulks telescope to allow students to see the night sky above Hawaii. Alison currently tutors A-level physics students online, including astrophysics, which she tells us is her favourite topic. Alison has given talks on various aspects of astronomy, including the marvellous mysterious moon at Bristol Cathedral, and has contributed to the Bristol Astronomical Society's Young Persons Astronomy courses. She is the secretary of the Bristol Astronomical Society and has been a member of the Society for about 10 years. So, with no further ado, I'd like to hand over to Alison on the subject of The Secret Life of Stars.
Okay, so Secret Life of Stars then. Right, the first thing about stars that we need to know is how they're formed, really. And I've got a little bit of video that I made some time ago, which I would like for you to watch. It's in the form of a bit of a story. Once upon a time, a star exploded. It was a huge star. The explosion of a star is called a supernova, and a supernova is one of the most energetic events in the universe. We've not seen any supernova in our galaxy recently, but a supernova caused the Crab Nebula to appear in the sky about 1,000 years ago. It was recorded in ancient China. The explosion resulted in a huge amount of dust and gas ripping out into space and causing shockwaves in the surrounding nebulae. The star that exploded in our story was the mother of our sun. The shockwaves from the explosion caused the gases and dust in the region affected to clump together, and the clumps attracted each other due to the gravitational forces between them. So the clumps joined into bigger clumps, and as they fell towards each other, they moved faster, and the ball of dust and gas got smaller and started spinning. As things get closer to the center, the spin speed, called the angular velocity, gets faster. Watch this ice skater bring their arms and legs in towards the center of the spin. As they do that, the spin speeds up. And this is what happened to the ball of dust and gas that ended up forming our sun. When squishy things spin, they flatten into a disc. Look at this koosh ball spinning and see how it was round, but as it spins fast, the ball flattens into a disc. So the ball of gas that was going to form our sun flattened into a disc. It's called a protoplanetary disc. This image was taken using microwaves of a protoplanetary disk that we can see now. This object is not visible to our naked eye. It's warm, but it's not hot enough to give off visible light. As the gas in our dust cloud continues to fall towards the center under gravity, the particles speed up. Here you can see some water droplets that have been caught using a strobe light. The strobe light flashes, and as the drops fall, you can see that the drops are further and further apart the further down they get. This shows that the droplets are accelerating, they're getting faster as they fall. And the same is true of gas that's falling towards the center of the dust cloud. The gas particles go faster and faster. So the central ball of gas gets more and more mass, and more dense, and hotter, until eventually the gas particles are moving so fast that when they collide, they fuse together. This is called nuclear fusion. And nuclear fusion produces heat. So the gas gets even hotter, and the particles fuse more. And the ball of gas gets even hotter, and the particles fuse even more. You get the idea. The ball of gas is now so hot that it lights up. Ping! And you have a star. What is left spinning around the star in the disk eventually gets pulled into clumps, and we call those clumps planets. This process is not neat, and it takes a long time, and the lumps can collide with each other and knock each other out of orbit and pull on one another. Eventually, the whole system settles down so that the planets move around the central star in regular orbits. The outermost planets move slowly, and the inner ones move faster. They are all moving around the sun in the same direction and are on approximately the same plane. We call this plane the plane of the ecliptic. This is the result of forming from the same spinning dust cloud, so all the planets go round the same way. Okay, so that is how a star like our sun is formed. And let's see if I can step onto my next slide. There we go. And this is a model of a gas. So now obviously this is a gas in a box, and obviously the box isn't there with the star, it's held gravitationally. And the gas particles are all moving about randomly, but if you heat them up, what happens? The particles move faster. And if you look at the top, can you see the pressure is going up? It goes up. And those particles, they all collide with one another, and they push. There's a push outwards. They're moving faster. They hit one another more often. They collide with one another. They push one another apart, and that outward push is what stops the star from completely collapsing under its own gravity. And so this gas pressure acts outwards, and gravity acts inwards. So in a stable star, and our sun is a stable star, you've got two forces: gravity, which is acting on every mass, and that's pulling in. And then the fact that this ball of gas is hot, the particles are bashing into each other and trying to force one another apart, and that's pushing out. And those two forces balance one another perfectly in
lots of stars, and that's what's happening in the sun. And when a star gets to that point where those two forces are beautifully balanced, then it can stay in that state for a very, very long time. And what's happening inside the star is that you've got hydrogen, which is the main bulk of the gas that was in that dust and gas cloud, is colliding with itself. And hydrogen atoms, when they're this hot, and they are very hot in the center of a star, there are no electrons attached to them. So a hydrogen atom becomes just a proton, a positively charged particle. And they have to be going very fast in order to actually fuse when they join together, because positively charged particles, they repel one another. Like charges repel. You remember your GCSE science. So you've got to overcome that repulsion, which is quite a significant force when they're that close together. And so they have to get really close. They force them together, and then nuclear fusion can happen. And the force, there's another force. It's very strong. It's called the strong force, which is bigger than the electrostatic repulsion that's pushing them apart, holds them together. And hydrogen turns into helium. So if you've got 2 protons in a nucleus, then it's helium. If you've only got 1, then it's hydrogen. And if you've got 3, then it's lithium. And if you've got 4, then it's something else. So and this is so the stars, they make the elements. So we've got hydrogen is fusing to make helium. And I don't know, can you remember this equation? I hope you can. This is Einstein's famous equation. What it says is not that energy is converted into mass. What it says is that energy is mass. And what we discover is that the mass of the helium that we make is less than the mass of the hydrogens that went to make it. In other words, there's a difference in the mass, and that mass is energy, and that's the energy that the star is radiating out fiercely in all directions. This is where the energy from stars comes from. It's nuclear fusion energy. So this is not like a chemical burning. This is creation of elements inside stars, and one of the side effects, one of the products, is heat. And this is where this energy, this outside, the gas pressure keeps the gas hot in the middle of the star. It might be many millions of degrees in the middle of the star. The outside of the star, different kettle of fish altogether, but the middle of the star, very, very hot indeed, in order that nuclear fusion keeps it hot, and that's where the energy comes from. It comes from this difference in the mass between the hydrogen that we started with and the helium that we've made. And eventually, of course, a star will run out of hydrogen, which is what happens, and Phil's going to talk about that later on. So at the moment, we've got lots of hydrogen, and the star is stable. It's fusing, it's giving this heat, which is causing the outward pressure, balancing the gravity. Yay! Really good. We're lucky that our sun is stable, and it's going to be stable for quite a long time, about another 4,000 million years-ish before it does anything different. And it's called a main sequence star. Okay. So at this point, what I'd like to do is I'd like to mention a little bit of a problem that we've got. Okay, and the problem that we've got is that we have to describe how bright stars are. I mean, this is one of the things that astronomers do quite a lot of, actually. And we've got various different ways of describing them, and there are problems with all of them. And I just thought that I would mention this because we've got luminosity. So luminosity is kind of like a measure of how bright it is. Yeah, you'd think that would be good, wouldn't it? Well, luminosity is measured in watts. So it's exactly the same as power. It's the amount of energy that the star is kicking out every second, right? Or you can measure brightness. Well, brightness is kind of like it's a bit of a movable feast. Well, how bright does it appear to be? And of course, then you come on to actually putting numbers to brightnesses, and we call this magnitude. And there's the apparent magnitude, so how bright a star appears to be from us here, where we're looking at them from, which is on Earth, because we can't go anywhere else to look at them from. And then, of course, there's the absolute magnitude. So you might have a star that's really, really, really bright, that's absolutely humongous and kicking out lots and lots and lots of energy, but it's a very long way away. And so it doesn't feel, it's not as bright for us to look at as a much smaller star, but that's much closer to us. So then you've got not just apparent magnitude, how bright it appears to be, but absolute magnitude, which is how bright it would be at fixed distance. Okay, and then we've got intensity, which is the power arriving per unit area, or relative intensity. So you can say, well, the sun's intensity is this, and it's twice that of the sun, or something like that. So, and then there's power density, which is the energy per, it's a complete minefield. Okay, it's made worse by the fact that these scales are not linear. Then you don't double. The star that's twice as bright to look at doesn't have twice the power coming out of it, and it's horrible. That whole thing is a complete can of worms. So I just thought I'd mention that. Right, moving on.
Now, the whole.
I want to go back. Right, okay. So this next bit, I need to say to you. Okay, this next bit is about black body radiation. So the star, I know it seems odd, is a black body. And this becomes really, really important, because one of the ways that we categorize stars is by the color that they are, which indicates temperature. Okay, and so this next little sequence that I've actually cut out of one of my A-level physics sessions is it's about a black body, and a star is actually is pretty close to being a black body. So, and it's really quite ironic that the closest thing we've got to a black body obviously isn't black. I mean, stars are not black, right? They're very bright. So I want to explain about what a black body is, and that's what this next sequence says. So a black body is an object which absorbs all of the light landing on it. Okay, and that's actually quite a difficult thing to do, because I mean, light is reflected. The reason you can see me is because light from the lights above my head are reflected off me. They interact with me, and they're reflected off me, and that means that you can see it because it's coming into your eye. Virtually every object reflects some light. Even really, really black things reflect some light. And so thinking of a model for an object which doesn't reflect any light of any wavelength at all is quite difficult. And that's what this next sequence is about.
Now, the whole, just the whole.
So this is a box with a hole in it.
It's a black body.
And the hole is the black body.
Which is an odd thing to say. I mean, it's a thought experiment, this. So now you're beginning to understand what a black body is. There is nothing there, because it's a hole, for the light to be reflected from. So the light just goes straight in, no matter what wavelength it is. And then inside there's an arrangement which makes it get absorbed. So that hole is a black body. Right, now, the next thing to say is, what would happen if you were to heat up this box? You heat it up and you heat it up and you heat it up, and eventually, let's suppose it's made from iron, and just like an iron horseshoe, you get it hot enough and it will start to glow. It would start to glow red hot. Okay, so in that situation, can you see that sunlight would start to be emitted from the hole? The hole, however, would still absorb any light falling on it. It just also happens to be emitting light. So the hole is still a black body, even though more radiation is coming out of it than is going into it. And this, in essence, is what stars are. Now, a star
is not see-through. You can't see through it, but it will allow light to escape from it. And it behaves exactly like the hole in this box. It's hot, which is why it emits more light than it's absorbing. But if starlight from other stars lands on the sun, it will absorb that light. I mean, okay, it's not very intense, but I promise you that it will absorb it. So, so the sun is a black body, and in fact, all stars are. As a star gets hotter and hotter, the wavelength of light that it emits goes more and more towards the blue end. So if you imagine a horseshoe being heated up, it gets red hot to start with, and then if you carry on heating it, it'll get sort of orange, and you carry on heating it and it'll go yellow, and you carry on heating it and it begins to glow white, and eventually, if you got it really hot, I mean, apart from melting, it would be blue-white. Okay, so now we're getting into this idea that the temperature of something is indicated by the color that it is. And this was a really important piece of work that was actually relatively recently done. And what they discovered was that the peak wavelength, so can you see this top graph, the peak wavelength is it's sort of green or yellow, and it's in the visible. And in fact, the sun, it's a little bit hotter than that. It's more slightly more green. Has a peak wavelength, so the most intense wavelength that it gives off is it's a sort of a cyanish green. So technically the sun is green, but of course actually it's white because it gives off all the colors of the rainbow. When you mix all the colors of the rainbow, you get white. So the sun is white, but its peak wavelength is in the green. Anyone would think that we have evolved here because that's what our eyes are most sensitive to. It's green light. So the sun is kind of that from that peak wavelength, we can tell the temperature of the surface of the star. Okay, and can you see that that as you go cooler, the peak wavelength moves to the right, and so longer waves, redder waves, are to the right. So cooler stars are redder, and warmer stars are hotter. Okay, they're bluer. Okay, so hotter stars are more near the blue end, and cooler stars are more near the red end. So just from the color of the star, and any astronomer worth their salt will tell you that you can actually see the colors of stars. That it's very noticeable, for example, that Betelgeuse is a sort of yellowy orange color, and Rigel, which is a really, really hot star, is a kind of blue-white. And you can actually see it with your telescope if you look at the stars. From the color, you can tell the temperature of the surface of the star. Now, this is not the middle, this is the surface of the star. Okay, so this is black body radiation, and stars are black body radiators. Okay. Why won't it move on? Go on. Move on. No. Oh, it seems to have crashed. Hang on. Oh dear. I'm sorry about this. Let me try again. Is that going to work now? Come on. There we go. Woo! Too far. Sorry, apologies. So now this is how stars are classified. Okay, so these are usually in the other order. So O is the really bright, hot, very hot stars, and they're usually really big because in order to produce lots of high temperature stuff, lots has to be going on inside, all that nuclear fusion. So they're really big. So O stars are really, really hot, and don't ask me why they're like this. They ought to be in alphabetical order, but they're not. O is the hottest and the brightest and the bluest, and then B can you see, is it's white to blue white, and then A is described as white, and F is described as yellowish white, and G, which the sun is a G2 star, is described as yellow. Okay, it's actually white, but it's yellow. And then K is orange, and then M stars are red. And you can see that most M stars are small. They're called red dwarfs, and they're very small. But there are some stars that are absolutely humongous and red. And the reason that they're red is because they've swelled up. And in swelling up, they do work, and that means that they cool down, and so the surface goes red. So, and they're called red giants. And so there are some really, really big red stars.
Alison, 2 minutes, please.
2 minutes, yeah. I've got one more slide to go. No, two. Okay, so this is about the codes, the classes O, B, A, F, G, K, M, and I always remember them as O, B, a fine girl or guy, kiss me. Okay, that's how you remember them, and they've got temperatures associated with them. And then, of course, that actual astronomers don't tend to do that. They use something called colour index. And this is, I mean, basically, the bigger the number, it goes negative, but the bigger the number, the cooler the star. And it's just it's a comparison of looking at the star through two different filters. So B is a blue filter, V is visible, meaning green, U is ultraviolet, R is red, I is infrared. So you're looking at the star through two different filters, and you're comparing them, and that gives you it's called a color index, which just makes everything even more complicated. And then we get on to the Hertzsprung-Russell diagram. And this is really, really important piece of science. And I love this one because it's so colourful. So the main sequence, which is this diagonal line down the middle of this diagram, these are stars that, like the sun, have got this stable outward pressure, inward gravity pull. And those stars are described as main sequence. And most stars are there. All the other stars around here and around here are either very, very big or very, very small, and the temperatures are that you can see that to the right they're cooler, redder, and to the left they're hotter, bluer. And this Hertzsprung-Russell diagram is a plot of the luminosity, so how bright it is. So the hotter, bluer stars, the bigger stars, are much brighter, and the really big stars are all at the top because they produce a lot more light and heat, but a lot more light. And over on the at the bottom, we've got wavelength. So the wavelengths are getting longer as you go towards the right. So the colour is getting redder as you go towards the right. So this is how we classify our stars. And I believe now Phill is going to talk about things moving about on this diagram, because stars, as they age, they can move about into different regions of this diagram. Right, and that's it. That's my secret life of stars.
Well, thank you very much, Alison, for a great talk. You've explained some of those secrets to us, so thank you very much for that. Feel free, everybody, to give a little bit of applause.
Thank you.
Thanks very much. Right, we'll come back to a couple of questions that have come in, I think, towards the end of tonight's sessions, as time's a little bit against us. So I'd like now to move on to our second talk for this evening, which is entitled The Death of Stars by Phill Wallace from the Cardiff Astronomical Society. Now, a few words about Phill. Phill has had a lifelong passion for astronomy, sparked by his grandmother buying him an I Wonder Why encyclopedia at age of 3, so he tells us. Since then, he has studied astronomy for his degree at the University of South Wales, and almost by accident joined the Cardiff Astronomical Society in 2015. Unable to suppress the volunteering gene inherited from his mother and grandmother, he joined the Cardiff Astronomical Society committee later that year and took over as chairman in 2016. And then in 2019, was elected as a Fellow of the Royal Astronomical Society. Phill has written and delivered talks to many societies in South Wales and beyond, and I stress these are his words. He will happily bore his colleagues by talking about space at every opportunity. Well, I'm sure, Phill, you're not going to bore us tonight, so we look forward now to listening to the death of stars. Thank you.
Well, thank you, Stephen. Good evening, everyone. Most of you, some of you from the Cardiff lot will know me, and the Bristol lot might recognise me as well from a couple of talks there. So I've sort of drawn slightly the short straw on this one. Alison has rather wonderfully explained how stars are born and what they do when they're alive. I get the somewhat morbid task of telling you what happens when they die. So there we go. So again, it's a topic that comes to all of us in the end, old age. I'm coming up to my 32nd birthday and I'm already feeling it. So Alison was explaining how in the core of the star you have all that hydrogen being consumed and turned into helium and energy. Now, only in the core is the temperature and pressure high enough for the fusion to happen. And obviously there's only so much hydrogen there given the star's lifespan. And when the fusion fuel runs out, the star moves off that main sequence that Alison showed you at the end there with the Hertzsprung-Russell diagram, and the star begins the inevitable decay. It moves on to either the giant or the supergiant branches, and where it goes depends pretty much entirely on its mass. So here is a nice little graphic of the life cycle of a star. So as Alison said, we start from the stellar nebula, and then you have average stars. So our sun, bit smaller, bit bigger. They will then swell up into red giants, which will then form something called a planetary nebula, which might be one of the worst named objects in astronomy because it doesn't have anything to do with planets. And then finally, that will end as a white dwarf, and then finally a black dwarf, which is not shown on here. The really big stars, on the other hand, that are 10, 20, 50, 100 or more times the mass of our sun, they will live much shorter lives and much more violent deaths. They will swell up into red supergiants like YB Canis Majoris or Arcturus, or indeed Betelgeuse that you saw in that size comparison video at the start. They will then end their lives in a cataclysmic event called a supernova, which will leave behind a neutron star or a black hole. So the low mass stars, this is what's going to happen to our sun and similar stars. The sun has enough fuel in its core that it will be shining for about 10 billion years. We're about halfway through that lifespan. Once that hydrogen fuel in the core is exhausted, the outer layers of the star will swell up and expand, destroying nearby planets. Depending on exactly which prediction you read, our sun will destroy definitely Mercury, definitely Venus, probably Earth, but Mars might get a reprieve. So it's going to become a very large object and destroy everything in the meantime. The core, meanwhile, will collapse inwards. It'll, with none of that outward gas pressure that Alison was talking about, the gravity will compress it further, which will increase the temperature, which will increase the pressure, and at a certain point, it gets high enough that the helium nuclei can start fusing together. I just realized I'm not sure why I'm gesturing with my hands here because you're not looking at those, you're looking at the PowerPoint. Anyway, so the helium will start fusing together into specifically carbon, which is not the next element up on the periodic table. It skips over lithium, beryllium, and boron and gets to carbon because that is 3 helium-4 nuclei forming together into carbon-12. And that's as far as most stars will go. Now, the helium will fuse to carbon, sometimes oxygen, something called the carbon-nitrogen-oxygen cycle, which is where those elements come from. Unfortunately, once that fuel is exhausted and there's no more helium, then the star is dead. It's not massive enough to generate the temperature and pressure to fuse carbon, nitrogen, oxygen into heavier elements. So that's as far as they go. The outer layers will then escape outwards completely, forming that terribly named planetary nebula, whilst the core collapses into something called a white dwarf. Now, we'll come back to white dwarfs in a bit when we get to stellar remnants, but now for the exciting ones, the high mass stars. So these are the much heavier, much hotter than our sun, and they live much shorter lives. You probably all heard the expression burning a candle at both ends. Stars absolutely live this. That will live fast, die young. Because they're so much heavier, the gravity is a lot stronger. So the core has to, the fusion reactions in the core have to generate a lot more energy to balance that gravitational pull, which means even though there's more fuel there, it's not a strictly linear relationship. So whilst there's more fuel, it's burning that fuel at a much faster rate. It seems to be, there is a crude little approximation that you basically take 10 billion years and then divide by the cube or the third power of the mass of the star and solar masses. So a 2 solar mass star will live about 1.25 billion years, and it just shrinks down. The really big ones might only actually be on the main sequence for a few tens of millions. So these stars, they will go through the same process. The hydrogen fuel will be exhausted, the outer layers will expand, the core will contract. The core will then start fusing helium into carbon. That sustains the star for a little bit longer. Once that's done, the core will shrink again. You'll start fusing heavier elements. Not all the stars will get further and further up the table. Some will only go so far, some will go all the way. Each of these fusion stages is shorter and shorter than the previous ones. And this is because the higher up the periodic table you get, fusion generates less and less energy. Hydrogen generates the most, helium less so, carbon less so, and so on. And eventually, the core, which has shrunk and shrunk and shrunk, will be made of iron 56 to be precise. And this is the tipping point. Fusing iron into something heavier takes energy. It doesn't generate energy, it takes energy. And at that point, that's game over. So for the really big stars, they wind up looking something like an onion. You will have a big outer envelope containing hydrogen. And then at the core, you'll have a shell that's got helium that's fusing to carbon. Within that will be one that's fusing carbon into neon. Within that will be going to oxygen. Within that will be going to silicon. And then finally, the core will be iron. Now, as I said, each stage takes less and less time because you're getting less energy out of the reaction. There's also less fuel in each stage because it takes 4 hydrogen atoms to make 1 helium atom. It takes 3 nuclei to make 1 carbon nuclei, and so on. So you get less energy, there's less fuel, and you're still trying to generate the same amount of power. So it goes faster and faster and faster. In fact, according to most of the models, that last stage where it's fusing silicon to iron will last for perhaps 3 minutes. So less time than I've been talking, a big star somewhere is dying. So the core is now solid iron, and it's a chunk of iron that's bigger than Earth. So it's a big lump of metal. Suddenly then, no more fusion, no more outward pressure, gravity takes over and the outer layers collapse inwards at very high speed. The core, however, is a gigantic lump of solid iron at very high densities. You can't compress it anymore. I mean, if you ever messed around with the syringe, you can compress gas quite a bit. You can barely compress liquid at all, and trying to compress a solid with your bare hands is just going to fail dismally and make you look foolish. So these infalling layers will hit this core and then be reflected outwards again. They will effectively bounce. This is the supernova explosion. But it's very important because in this sudden thing, suddenly you've got a lot of lighter elements that are compressed and can suddenly fuse. You've also got, so you get even more stuff like silicon, calcium, and so on. You've also got an awful lot of neutrons flying around, which can then merge with the other heavy stuff that's coming out to produce stuff heavier than iron. So copper, stuff off the top of my head that's formed from supernovas. Copper, tin, mercury, cadmium, stuff like that you probably only recognize from batteries, tungsten, and so on. All of that's formed in this process, but there's lots of neutrons, very rapid nuclear decay. This is your supernova explosion. This will destroy anything else in the star system. If there is anything there, it'll wipe it clean. Now, this is a very zoomed in image of that supernova onion diagram. So again, the core's collapsed, can't be compressed anymore, but the outer layers are still coming in, and you get that sudden reaction. You can almost think of it as like a really big shell-shaped nuclear explosion that's blasting this material back out again. So that's tremendously bright. And these supernovae can be visible during the daytime if they're within our galaxy. So the supernova that Alison mentioned that formed the Crab Nebula was seen during the daytime by Chinese astronomers in, I think it's 1054, 1056, one of those two. Certainly quite a while ago. The average seems to be about one supernova per galaxy per century. So we haven't seen very many very close. The last really big one that I can recall was supernova 1987A, which was in the Large Magellanic Cloud, one of the satellite galaxies that was described in last week's talk. So the supernova is big, it's violent, but also, again, you've got this core which has generated all these heavier elements. So the carbon in your DNA, the oxygen and nitrogen you breathe, the calcium in your bones, the iron in your blood, all of that was manufactured in the heart of a dying star and then scattered out into the cosmos. So, and then at least another star had to die for those shock waves that Alison mentioned in the first talk to shuffle up the gas cloud and make it start forming stars. And some elements, like gold, for instance, are actually too stable to form in this process. They form from something else entirely. So, as I occasionally remind my colleagues, you are the result of about 3 billion years of natural selection, and 4 dying massive stars act like it. It's quite a useful statement, really, because it tends to shut them up. So, the star's dead. Most of the mass is lost and has been hurled out into the cosmos to eventually be recycled and form new stars, new star systems, new planets, new life. So it's the ultimate cosmic recycling system. But there is still that remaining core. Now, this is called a stellar remnant. And there are 3 known types. There is a 4th hypothetical one that falls in between the last 2. So white dwarfs, neutron stars / pulsars, and black holes. So then we'll throw those in order. The white dwarf then is what's left by the red giant star. This is what our sun will become. So it's the lowest mass of the stellar remnant of the 3, but it's physically the largest. They're very, very dense, and they're very, very hot. So a white dwarf, the mass of our sun, is about the size of Earth. But again, you've got something the size and mass of the sun shrunk down to this physical size of the Earth. That is a very rapid, massive increase in density. The surfaces will be temperatures of anywhere between about 10 to 30,000 degrees. Now, you may recall that Hertzsprung-Russell diagram that Alison showed you, and you had all the white dwarfs in this little corner at the bottom left, where they were really, really hot, but they weren't very bright. And that's because the surfaces are very hot, but they're not generating any more heat. They are just slowly cooling down. It's the most common one you'll find. About 97, 98% of the stars in our galaxy will end up as white dwarfs. Eventually, over a very long time period, they will have cooled down completely and they'll no longer be visible, at which point they will become black dwarfs. However, the universe is, to the best of our knowledge, not old enough yet for any black dwarfs to have formed. Oh, that's actually just what I explained. Now, these are very, very common in binary star systems, these sort of two or sometimes more star systems that, again, we talked about last week. Now, this can lead to what we call a type 1a supernova. Supernovae are classified by types. So you have type 1a, type 1b, type 1c, type 2, and there's a bunch of subtypes in that. You would think that type 1 is this one I'm about to describe with white dwarfs, and type 2 is the massive stars collapsing and exploding. Actually, no. Type 1a is the one with white dwarfs, type 1b, type 1c, and type 2 are all the massive core collapse supernovae. They're split up into type 1 and type 2 by their spectra. So when we look at the object, the supernova, we can see what elements are present. If it has hydrogen in the spectra, it's a type 2, a big star dying. If it doesn't have hydrogen, it's a type 1. Type 1b and type 1c are some like weird special cases of really big stars collapsing. But again, it's another example of the, shall we say, non-obvious naming conventions we use as astronomers. So one last blast for the type 1a. So in a binary system, and this is an artist's conception of something called an object called RS Ophiuchi, if the two stars are close enough, the white dwarf will slowly pull material away from the companion star. Excuse me. And this hydrogen will then settle in a layer, because again, being very, very small but very heavy, the white dwarfs have very, very strong surface gravities, way beyond Earth, Jupiter, the Sun, anything like that. So this hydrogen will settle onto it, and it will wind up in a spherical shell until eventually it will reach a certain mass, which is variously sized as either 1.38 or 1.44 times the mass of the Sun, called the Chandrasekhar limit. And once it crosses that limit, it will collapse into the neutron star. And this is a particularly quite nice violent event, and this is the type 1a supernova. The reason it collapses is the white dwarf is not generating radiation or gas pressure to counteract the gravity. It's held up by something quite complicated and rooted in quantum mechanics called electron degeneracy pressure. So it's a quantum mechanical effect that's preventing it collapsing further. That only lasts up to a certain mass, the Chandrasekhar limit. Once that is exceeded, it collapses further into the neutron star, which is the next object we will come to. So the type 1a supernova, they are very, very bright. In fact, here is supernova 1994D in a relatively nearby galaxy. You can see how bright it is there, and that is several tens of millions of light years away. These supernovae are very, very useful for astronomers because it's always the same intrinsic brightness. So we know how bright it should be. We know how bright it appears to be to us. And from that, we can work out the distance of not only the supernova, but the host galaxy as well. Anywho, neutron stars. Now, these are the next step up. They will form from supernovae of either type, either the massive star collapsing or the white dwarfs gathering up matter and then collapsing themselves. These are even heavier, but they're even smaller. They are 1.5 to 3 times the mass of the Sun, but they're only about 20 kilometers across. So this is something that might be twice the mass of our Sun, but would fit between Cardiff and Bristol with room to spare. That's the sort of scale we're looking at here. They are formed almost entirely of neutrons. So the electron degeneracy pressure hasn't worked. It's not lasted long enough. The electrons and the protons have then combined in an inverse beta decay, and the charges cancel out, and that leaves neutrons. And these neutrons, which are normally close but never touching in atoms, are now almost physically in contact with each other. And quantum mechanics doesn't like that at all, which is what's holding it back this time. So because it's almost entirely neutrons, you can think of a neutron star as a single gigantic atomic nuclei. It's absurdly dense. There's something the size of a matchbox, or I suppose a phone nowadays is probably a better comparison, would be 3 billion tons or so. So, something that will fit in your pocket would be the same mass as a good-sized mountain. These will form during the initial stage of that supernova. So the iron core will collapse and it will hit the neutron star stage, and that can't be compressed. Again, they will rotate very, very fast. It's that conservation of angular momentum thing again that Alison mentioned, except this time they are shrunk down even more. You've gone from something that might be 100 million kilometers across at the very end of its supergiant stage that shrunk down to 20 kilometers. It's spinning very fast. 6,000-7,000 revolutions per minute is not uncommon for these. The fastest ones are spinning so fast that the equator is moving at about a quarter of the speed of light. Now, that extremely fast rotation combines with an extremely powerful magnetic field that the neutron star has, another relic of its parent star. And this produces I believe it's Bremsstrahlung, braking radiation. It's, again, another very technical term. Essentially, where if you have these motion and magnetic fields interacting, you can get very, very powerful radio emissions. So radio frequency radiation being emitted out along the poles of these rotations, like a lighthouse in space, but in the radio frequency. And if that axis of rotation passes across Earth, we get a regular beep, beep, beep in the radio telescope. In fact, when these were first found in 1956, I think it was, or 1966, anyway, 50s, 60s, that time, by Jocelyn Bell, it was such a regular and consistent signal that they actually noted it as LGM for little green men, because they didn't think it was natural, which is, not an unreasonable assumption at the time. So, yeah, as I said, they have very fast rotations and they have very strong surface gravities. I actually worked this out once. If you were standing on a surface of a neutron star that's twice the mass of the sun and weren't crushed into a paste, I could drop a marshmallow from shoulder height and it would be so rapidly accelerated it would hit the ground with the same force as the bomb dropped from Hiroshima. And that's a marshmallow. These will form from stars that are at least 10 solar masses. So you see how much mass is lost, though. 10 solar mass star leaves behind a 1.5, 2 solar mass neutron star. That's 8 suns worth of material scattered out into the cosmos to form new stars. But now, sometimes a star is just too fat. The Weight Watchers scheme hasn't worked, and the star is just too big. A black hole is their fate. The core remnant from the supernova, that massive lump of iron and heavier stuff, collapses into a neutron star, but the neutron star, it's above the threshold where even that neutron degeneracy pressure can't hold back gravity. And gravity, what is normally the weakest of the 4 forces, suddenly becomes the strongest, and it finally wins. And it will just keep collapsing and collapsing and collapsing into, we don't know. There is no way for us to know what happens inside a black hole. Things get really, really weird. So next we have an artist's conception of a black hole. Now, this artist clearly thought he was funny, so I refused to pay him and decided to get a simulation instead. This was released by, I believe this was done by someone at MIT in 2019. In the center there, we have the black hole itself. This was called the event horizon. And that's the point of no return. At the event horizon, the escape velocity, how fast you have to go to get away from the black hole, becomes equal to the speed of light. And since you can't go faster than the speed of light, once you're inside the event horizon, there is no coming back. The material around it is called the accretion disk, and this is material that is slowly falling into the black hole. Eerily similar to that protoplanetary disk that Alison mentioned in the first talk. The reason it's distorted like that is on the far side of the accretion disk, the light is going straight up, but is then curved around by the gravity around the event horizon to come to us like that. So the light is being bent 90 degrees. Now that's a scientific simulation. And when I wrote this talk originally, this is a adapted version of one I first wrote a few years ago, this was as good as we got. I honestly could stand up and say, we won't ever get a picture of a black hole. I don't think it's physically possible. Well, the Event Horizon Telescope team went and proved me wrong. This is the supermassive black hole in the heart of the galaxy M87. This is an actual image gathered with a bunch of radio telescopes over a 2-year period. And I think this was something like 5 million gigabytes worth of data to produce this image. And it matches up almost exactly with that simulation. You've got the shadow in the center, which is the event horizon. You've got the accretion disk around it, where one side looks brighter because it's being bent around and focused to us. I mean, I remember this was front page news. You walked into the corner shop that morning, and every single paper, with I think the exception of the Sun, ironically enough, had this on the front because this was a big deal. Then, a few years later, they went and did it again. So Tiffany in the chat asked about the massive black hole Sagittarius A star in the heart of our galaxy. Here it is. Same team, same method. And again, about 2 years worth of data. It looks a lot brighter because the black hole is physically, the accretion disk is a bit smaller, but it's also a lot closer to us, so you get a bit of that effect as well. So then, as I said, once you hit that event horizon, nothing can escape. Light cannot come out again. I've said here it's infinitely dense. The laws of physics sort of break down a bit when you hit the event horizon, or at least as we understand them. We model the black hole as if it's a single point mass, so it doesn't have a width, a depth, a length, or anything like that. And because it doesn't have a volume, it then is infinitely dense. Whether that's actually true or not, we don't know.
2 minutes, please, Phill.
Thank you. I'm almost there. That's good timing. So when you're approaching the black hole, if you are, for some reason, dumb enough to fly towards a black hole, you will be ripped apart by something called gravitational tidal forces before you reach the event horizon. Essentially, the gravity well that you're falling down, the slope, if you will, of space-time, gets so steep that the force pulling on your head might be 50 newtons, the force pulling on your feet might be 150 newtons. So you get stretched out. And this is the one truly brilliant technical term we have in astronomy, and it's called spaghettification, or sometimes the noodle effect. Now, you hit the event horizon and that's it, game over. We can't explain what's inside. In fact, the only things we can know about a black hole is its mass, its rotation, and whether it has an electric charge. In theory, that's all we can know. How we actually measure the electric charge of a black hole, I don't know. So we can't see the black hole itself, but we can see the accretion disk around it. We can also see these bright jets of matter that come out of it. And these can actually be some of the brightest objects in the entire universe, which is slightly ironic. And now a somewhat maudlin topic to end on. Eventually, everything in the universe will be either scattered dust or black holes. The black holes themselves will theoretically eventually evaporate via a process called Hawking radiation, leaving nothing but scattered gas and dust, with no stars, galaxies, or light. However, when I say eventually evaporate, it will take many, many, many times the lifespan of the universe as we are now for that to happen. At the moment, any mass black holes lose from this Hawking radiation is made up by what mass they absorb just from ambient starlight. So for the moment, black holes will just keep getting bigger, but eventually that will be all that is left. We will leave the stelliferous era and become, I don't know what they've actually called the next era of the universe, but it will be cold, dark, and frankly quite boring. So, thank you very much.
Well, thank you, Phill, for another fantastic talk on the death of stars. I know that's generated a lot of interest and some questions too. So thanks again, and some applause for Phill, please. Okay, we've had some questions come in this evening. We don't really have time to cover them now online, so I'm going to ask Alison and Phill, please, to respond to those offline if you could. They're covering the subjects of the origin of the strong nuclear force, real versus false colours in stars, and white dwarf formation in a binary system. So we'll answer those in due course. Thanks very much for that. So thanks everybody for your attendance this evening. Thanks for asking those good questions. And as I mentioned, if other questions occur to you later on, please feel free to contact us or email us and put them online. So to conclude, our third session will be held on Tuesday, the 27th of February over Zoom. Again, 7:15 for 7:30 start. And the theme will be large scale cosmos, and an invitation will follow soon. So I look forward to seeing you all then, and goodbye for now. Bye-bye.